We are very happy to have Professor Spencer Chang from University of Oregon telling us about simple anomaly detectors for jet substructure. So please begin.
Okay. Thanks so much for having me. I had a really great time in 2019, December, when I went to Korea, and hope to visit again when in the future. So, and actually I was going to a workshop on machine learning at IBS. So this is, again, something about machine learning. And I see that, there's been some seminars on machine learning in this series. So there'll be some things I will kind of skip, but I have some backup slides if you want any more details. So this is work that's been done in collaboration with my student, Lane Bradshaw, and Brian Ostick, who he was a former University of Oregon postdoc. And he unfortunately left, well, he's probably making tons of money. He left the physics to go to Microsoft. So this was our final physics project. And so as was said, I'm going to describe what anomaly detectors are for jet substructure and how you might be able to design a simpler version of them, with the kind of added benefit that you can understand a little bit more what the kind of information they're relying on. So it's a little bit like the analogy I'm making with the clock is, if you had the clock and it's was completely obscured, you would just know that it kept time really well, but you wouldn't understand why it did, right? You wouldn't understand that below there's this precise set of gears that have been designed so that it maintains this. So in the same sense, machine learning and neural networks tends to be like a black box. You understand they work well because you can test them to see if, like, for instance, if you want to pick out signal versus background, but it's really important to try to understand them. Okay, so this is in that vein. Okay, but let me start more generally, and you don't need to be convinced of this, but machine learning is becoming a very important kind of component of people's research in high energy physics. So on Inspire, I just searched for titles that had machine learning. And of course that, not all papers have machine learning in the title. And I was surprised that there was last year there were 342 papers. This went up from 7 papers back in, just 7 years or 8 years ago. So it's been a big explosion. I think we're on pace to pass this because we're only halfway through this year. And so there's a lot of people working on in high energy physics on machine learning. So this, of course, is not new, right? Like machine learning has been studied by experimentalists and used by experimentalists for a long time. But the kind of broader use by, research done by theorists and also in physics outside of particle physics, it's really been kind of mirroring the increase of machine learning done in computer science. So, and specifically to high energy physics, there are many applications. Signal background classification, which I'll talk about. Particle tagging, which I won't. Event generation, making faster detector simulated events. And anomaly detection, well, I'll also talk about. Okay. So, so I guess this is, well, we didn't have the title, but what is one of our okay. So the kind of the more specific thing I want to talk about is that machine learning, there's been a big emphasis that we need to understand how the algorithms work. So sometimes it's called explainable machine learning. So you have this kind of provocative robot who's now doing math and probably proving or calculating things. But we're not at this stage where the robot, the algorithm can tell us what are they using? How did they do it? They're not like a scientist that we can talk to. And for the general machine learning community, there's many reasons to understand the algorithms and how they're working, right? You might want to understand how they can be improved. In the US, it's, since there's laws against, bias and things like that, you don't want these important kind of algorithms that are being utilized more and more to have any kind of bias against certain races or gender, et cetera. And So there's these kinds of reasons why you might also be concerned about like, well, these black boxes working without understanding. In high energy physics, there's also a lot of reasons why we want to understand what's going on. Okay, so we certainly care about high performing algorithms, but we also value other aspects other than that they are high performing, right? So as from a kind of experimentalist point of view, we might be really concerned about what are the uncertainties on the inputs and the outputs of these, these neural networks. If you're doing this for an experimental analysis, you might want to propagate systematic uncertainty. So you really need to understand what's going on and what it's relying on. From a more theory kind of point of view, we can take this as an opportunity to learn from the machine learning, right? So machine learning is obviously outperforming some of our techniques that are kind of more human, physics driven, physics idea driven. And so we want to understand, can it teach us some things that we don't already understand about these problems, right? And I think this is a very, this obviously can work really well with ideas that are being generated in computer science, but in high energy physics, we have very specific concerns, certain kind of aspects that we really need to understand. And so it's important for physicists to work on this because we kind of know what we want to get out of it. Okay, so here's the outline for my talk. I'll be reviewing a technique that was proposed by these three authors, Fawcett, Thaler, and Whiteson. And they introduced a really interesting technique to produce a interpretable neural network classifier. Okay, so since we're modifying this technique, I'll spend a lot of time kind of like summarizing what they did and so that we can see how we need to adapt this to our approach. So what we're doing is modifying their technique and applying it to anomaly detection. They were also looking for signals in jet substructure, so we haven't changed the physics, kind of application, but now we're doing it for anomaly detection, so we're not focusing on any particular signal. So there's some kind of modifications that need to be made to do that. And it allows us to ask a very interesting question. So what they're proposing is a way to kind of get a more interpretable classifier that agrees with how a kind of a black box classifier where you don't quite know what it's using on how it orders events. So when we apply this to anomaly detection doesn't, you don't need to tell what signals you're interested in. It's only being trained on background events. So you can then figure out a way to make it, order background events in a certain way so that some are more anomalous than others. You can, of course, apply it to a signal, but it's never been trained on any particular signal. So what we're going to do is try to do the same kind of approach that Fawcett and company did, except we're going to be able to test it and see, okay, now that we know how, we mimic its order, we make a mimicker so that it can order the same way on background events, we can now test it on signal events and see if that transfers. So it's kind of it has a nice kind of test of, when we kind of mimic it on background events, does it agree with it when it transfers the signal events? Okay, and we'll see that it does largely work. And so this allows us to claim that we have a more interpretable, simple anomaly detector. Okay, so that's my outline and how I'll go about this talk. Okay, so here's the abstract and title page of their. Okay, so this is the abstract from their paper. And so when we saw this, we were really interested. You don't have to read the abstract. I'll kind of give you but the animation may be a little jarring, but okay, so what they're trying to do is start with a deep neural network classifier that is trying to distinguish. I think they were looking for W jets versus QCD. And here, you give it a jet image. It's supposed to spit out a number between 0 and 1. That it's 0 if it's a QCD jet, if it thinks it's a QCD jet, and a 1 if it's like a W jet. So some kind of boosted W inside this jet. Okay, so their technique does this. So it takes this complicated, unknown kind of black box classifier and replaces it with a different type of classifier where the inputs are very kind of interpretable, that they are these kind of high level physics motivated variables there'll be the energy flow polynomials, and I'll tell you what I'll review what those are. And there's going to be a finite set of these, like 6 or 7, to get kind of comparable performance between these two. It's still a deep neural network, but now the inputs are kind of physics variables that you know. Okay, so it will output some number G, and again, you want 0 to be background-like, and 1 to be signal. Okay, so I have to review a couple of things. I have to review, what are these inputs? How do I compare two classifiers and say that they are, agreeing, that this one is doing a good job of kind of imitating this one? And so let's go into those parts. And then the other key thing is, how do I find these variables and how do I build this up, right? So I'm going to do it iteratively. Okay, so that's the other key aspect of their approach. Okay, so the first thing is the inputs. These are the energy flow polynomials that Jesse Thaler developed with his students. So they are a nice basis for jet substructure observables. So it's both linear. So any jet substructure observable will be linear in them, but unfortunately it's infinite. So it's a little bit like a Fourier series, right? So the hope is that even though it's infinite, it's characterized by a few of the first ones and stuff like that. Okay, so let me review what they are. You can very easily kind of more naturally express them as graphs. Okay, so you take a graph that has no loops in it. So a graph has vertices or nodes. So if you label it, this node would be A, and you're going to attribute a sum to it. I'll come back to what this is. Then there are edges between nodes. So this edge connects A and B, the node A to node B. And there, for each one of these edges, you put in an angle variable between A and B. Okay, so this is a sum over all of the constituents in the jet. So you can either do this by calorimeter deposits, or by particles or tracks. You can a variety of choices of what you can do. So what is a ZA? It's for a hadron collider, it's most natural to use the momentum fraction of the transverse momentum. So of this object A, what is the fraction of the transverse momentum it has of the full jet? Okay. And so for each one of these nodes, you're doing a sum over the momentum fraction of each of these constituents. If there was nothing else, this would just sum to 1 because it's a fraction, right? But we'll add these angles. The angles is just the kind of the boost invariant, difference, square of the rapidity difference and the azimuth angle, right? So the natural thing you would use to define, angular differences in a hadron collider in a jet. Okay, so this is the correspondence. And so then if you gave me a graph, this is a complicated one, but just to illustrate the point, here's node A, B, C, and D. There's 3 edges between C and D. There's just 1 between these two, and then there are 2 between A and B. So you have a different sum for each of the constituents A, B, C, and D. And so here you just have the momentum fractions of each of those nodes. Here you have 2 edges, so you have 2 factors of that angle between A and B. Here between A and C and B, you only have 1 edge, and so there's just 1 factor of those. And here there are 3, so then you have these 3. So you can see why you don't want loops, because if you did this to itself, it would be multiplied by 0, right? Because the angle between it would vanish, and so it wouldn't give you anything non-zero. Okay, so this is a nice way to kind of categorize them and the energy flow polynomials. Okay, all right. Okay, so here now we want to, as we're building up a mimicker or an imitator of this classifier, we want to be able to decide if they're doing a good job. This G is doing a good job matching F. Okay, so how do they do that is define something called decision ordering. And really all it asks is, give me two events, x1 and x2. So this one might, take in the jet image of event 1 and the jet image of event 2 to get an f of x. Then the mimicker will take into some energy flow polynomials for event 1 and event 2. So even though they have the same x, they don't necessarily mean the same thing, same inputs. Now, imagine I have these two events. If f of x1 is bigger than f of x2, f thinks x1 is more signal-like than x2, right? If it's the opposite, f of x1 is less than this, it thinks x1 is more background-like than x2. Okay. Now, what I do is multiply the two differences, the differences of the f for the two events and the g for the two events. So if they have the same sign, this will be a positive number inside of this theta function. So if it's a positive argument, it says that f and g agree about the ordering of x1 and x2 in terms of their signal, how signal-like they are, right? Because if this is positive, then x1 is more signal-like than x2 from the point of view of f. And if this is positive for g, then g also agrees. It could be the other way. They're both negative. So they think that x1 is more background-like than x2, but they agree on the ordering. So this decision ordering is just saying, once I put the theta function, if they agree on the ordering, f and g, I get 1. If they disagree, so that they have different sign, then I get 0, right? And so I want to kind of, decision ordering just basically says, if the two classifiers agree on the ordering, I give 1. If they disagree, I give 0. It doesn't care about how much more, the magnitude of the difference. It's just the sign of the difference, okay? So it's really just saying, like, if I was just to order, the size of f for x1 and x2, is it the same as x1, for g of x1 and g of x2, okay? So decision ordering 1 says that they order in the same way, and 0 if they disagree. Okay, now the way to check if they are the same classifier on a set of events is to not just take pairs of events, but a distribution of events. So I can look at a distribution of events and get an expectation value of this decision ordering or average decision ordering. I integrate over the distribution of events 1 and 2. It might be drawn from the same thing. Like if you're just doing this on background, you could do background for x1 and x2. They would be the same distribution here. It could be signal and signal or signal background, right? There's a lot of choices, or you just mix them. But if this average decision ordering is 1, then on this distribution of events, f and g are effectively the same classifier because they always agree on the ordering of two events in that sample. If the average decision ordering is 0, it means they always disagree, right? They've always, every pair of events, they disagree. And if it's a half, then they actually, kind of randomly, agree sometimes and randomly disagree, right? So here, the best version is if it's 1, because they are effectively, f and g are effectively the same thing on these set of events. If it's 0, they actually order events in the complete opposite way. So actually, you could use minus g, and then f, if you had an ADO of 0, then f and minus g would actually have an ADO of 1. So actually 0 isn't so bad. It actually tells you just flip one of them and then you'll get a good agreement. And so it's really 0.5 is the bad value because even if you flip one of them, it doesn't agree. So the best value is if you get 1 or 0, and 0.5 is bad. So you should really do like 1, see how close it is to 1 or 0 to tell you how good this is. So this gives us a way to compare two classifiers, f and g, and if they kind of agree on the order. Okay, so now they have this coupled to an iterative approach to build this other neural network G. So if f is the one that I want to mimic, this is how you do it. So step 1, find over a list of energy flow polynomials, the one that would give you the highest average decision ordering, where you take the F and compare it to just the value of the energy flow polynomial for every event, right? So you can define not a neural network, but a decision, that depends on the EFP. So this is a very linear approach. It's just saying like, oh, does EFP1 kind of correlate with how F wants to order things, or right or not? So I'm just finding the linear correlation essentially with F that works the best here. But the step where I kind of still use a neural network to build up this mimicker is I learn that this variable is good. I then train a neural network, the first neural network, where the only input is this one that I've identified, this energy flow polynomial I've identified. So you train it just like the original F neural network, except you're building up what type of inputs you're allowed. So you're still giving it kind of the ability to use nonlinear information of the energy flow polynomials, but at least you know what's going into this black box. Okay. So now then, after you're done, you can compare neural network 1 to F, right? You can see, on the decision ordering, you can look at a sets of event pairs. You can find some that don't order the same way for neural network 1 compared to the one I want to mimic, the F neural network. And so take the pairs that are misordered by this neural network and just repeat the process. Now apply this decision ordering between F and some other new energy flow polynomial on the misordered events. Find this EFP2 that has the highest one. So it identifies the next input. Now we train neural network 2, where now it has 2 inputs, EFP1 and EFP2. And then you can just repeat until you are satisfied, whatever performance you're interested in. Maybe you're interested in that the final neural network has a very good ADO with the original neural network. Maybe you're also instead interested that you kind of only want a limited number of inputs, so it's more interpretable. So it's up to you kind of how far you're willing to go with this. Okay, so that's their iterative approach. Let's see how it works in practice. This is their, yep, yes.
Before that, can I ask a question?
Absolutely.
So is it any reason to using just a sign? I mean, the amplitude looks very important, in particular, if the F4G, the value is, there is many data which is F4G is 0.5 or something. I mean, which cannot distinguishable.
Yeah.
So is there any reason to use the sign?
Yeah. So you mean the theta function here?
Yeah.
So sometimes, so we were actually doing this for another example at the beginning where instead the inputs that we were trying to build this mimicker with were discrete. In that case, you're going to run into kind of degeneracies where this evaluates to 0, right? And then it matters what you define the theta function value at 0 is. I think the best thing to do there is 0.5. In general, though, as long as the events are like not identical, there will always be a sign difference between 2 events. And so I don't think it's that important to worry about like, the 0 aspect of this. But you might, so maybe you're asking that if f of x1 is much bigger than f of x2 versus, G thinks x1 and x2 are very close, should I kind of penalize this and say that G is not doing as well as F? I think on event by event, it doesn't matter, right? Because, that event, F, they still agree that, x1 is more signal-like than x2. And so I don't think the magnitude doesn't really matter. So another way to think about this is if there was a linear, if x1 was just a number, this is saying that if G was kind of a monotonic, related by a monotonic function to F, it would still agree on the ordering of events, right? And so those should still be considered the same decision, functions, even though they give different values.
Mm-hmm.
So did that I hope that clarified, but if it's still confusing, yeah, feel free to ask more.
It's also same if fx1 is close to fx2, but gx1 is very much bigger than gx2 or something like that.
Yeah, so this wouldn't care. As long as they're the same sign different, these two factors are the same sign, it would say f and g order these the same way. So you could think about doing other versions of this, but I think at least from the point of view of like a mathematical function of like ordering things, these are, this says I don't care about that.
Okay, thank you. Thank you very much.
Welcome. Okay, so let's see. Okay, so this is kind of their analysis. So I actually kind of, the step one was a little bit different here. When there's no EFPs chosen, they actually start with a neural network that's trained on the jet mass and the PT of the jet. Okay, so that starts here. You can already see that, the decision ordering between their, the black box, the F, which is called a CNN here, is pretty good already, right? You're already very close. 0.93. Well, we won't get numbers this high for our example. But from there, then they have three different approaches. The first one, the black box guided one, is precisely the technique I described, where you look over a set of EFPs, you calculate the ADO of kind of the mispaired events at step 0 to identify the new EFP you should add. Then you train a neural network, and this is so you jump from 0.92 or so to 0.96. Sorry, the blue, sorry, it should be almost 0.96, so you get the blue. And you just keep doing that, okay? There's two other approaches here. Orange is if you said, well, I want to get the optimal performance. I don't care about how long it takes. I should look at building up a neural network for each of the the energy flow polynomials that they generate, and pick the one that had the best ADO with the, the thing I'm trying to mimic. So this orange line should always be better than the blue line, and it is that. The problem is this is very slow, right? You have hundreds of energy flow polynomials. If you want to train a neural network each time for that, it takes a long time, right? So, and you have to do that at each step because, here there are 2 EFPs you need, right? 3, etc. And so it gives you better performance, but it's slow. Okay. Then there's this truth guided one, and which is a little bit kind of surprising, the result. The truth guided is don't compare the ADO to the CNN to find the EFP, but compare to what I know is when I give a signal, when I give a signal event versus a background event, I know exactly what it should be. Why should I match the CNN, which has its own definition of what's more signal-like and background-like? I could use the Monte Carlo that I know that some are signal events and some are as events. So it actually does better at the first step, but then clearly doesn't do as well for a little bit, and then eventually is as good as the black box one. It never gets as good as the brute force one. Okay. All right. So that's the 3 approaches. Let's see how this translates into using this to search for a signal, for the signal that versus the background. Okay, so what you would expect is as I get the decision ordering to agree better and better with the neural networks I'm creating, those neural networks should get better and better at finding the signal, okay? And so there's a metric called the area under the curve. I'll review it later, but 1 is perfect and 0.5 would be kind of the worst. And so here this dash line up top is the CNN that you're trying to match, right? So that's the best performance. The dotted line is kind of an approach that if you were, so they took what they call 6 high-level variables. And so they took some of the most commonly used jet substructure variables used in kind of you know, Atlas and CMS type analyses. And you can see that it does pretty well, but not quite as good. Okay. And so you would expect that, you know, by the time I get to 5, 6, or 7, I should be better than that by looking for this mimicker, because I'm trying to match this CNN. The brute force gets there quicker, right? It does it better already with 3 energy flow polynomials. With the black box one, it takes a little bit more time. By the time you get to 5, you've matched the 6 high-level variables that kind of are human derived, or kind of human sanctioned as good variables. And by the time you get 6, you're better, right? And you're almost essentially as good as the CNN. If you want to get that last bit, you can go to 7. And the truth guided one actually only does as well as the 6 high-level variables. Okay, but this shows that this works, right? It shows that, you know, this kind of very opaque, you know, CNN, which just takes a jet image, you're not quite sure what information it's using. If you are only interested in kind of getting as good performance of the signal and background, and have a limited number of inputs that you kind of more limited and understand, you see that 6 or 7 is pretty good, you know, by that time. Okay, so it's simplified the kind of inputs, and so it should be more interpretable. Okay, so that's the overview of the faucet technique. This is kind of like my first half of the talk, because we're going to now modify it. But are there any questions on this before we move on to the kind of modifications we'll do, because it'll rely on this technique heavily? Okay, I'm going to assume that there are no questions, that everybody's following along, but please feel free to stop if anything is still confusing. Okay, so we're going to, as I alluded to at the beginning, we're going to apply this to anomaly detection. So a nice motivation for anomaly detectors is, you know, machine learning is great, but you need to know what, you know, the type of classification I've shown before, where there's a signal in the background, you have to know what signal you're looking for. Now, wouldn't it be great if you could find a broad range of signals, but utilize the power of machine learning? So that's what anomaly detectors do. And you know, some of the, you know, for instance, this is used to figure out, like, if your credit card activity is anomalous, they might send you a warning that maybe somebody stole it and is using it, right? So in high energy physics, one of the most popular ways of doing anomaly detection is based on jet images. And so there are these kind of 3 groups. There's one at in Heidelberg with Tillman Plen. There's Rutgers with David Shee, and then there's this Caltech one with my name is her name is blanking. Well, Maria is purple. And so I'm going to be showing pictures from the Rutgers paper. So the rough idea is that you take a jet image, you go through something called an encoder, which compresses it. And there's some, you know, parameters on how compressed you want it, but roughly you're trying to take this image, compress it to some values, and then uncompress it, use the decoder to get an image that is as close to the images you want to train on. Okay, so the idea is you train this on QCD images of jets, you compress it, and you want to get, you know, a good representation. Of course, this isn't perfect. You know, you can see that it mostly gets these, you know, kind of hot spots the best. It loses a lot of this stuff, but largely it does okay, right? And so the idea is that, okay, I'm really designing this to be good at background events. Okay, so when you look at how the image here compared to this image, if I take each pixel, take the difference of each pixel, square it, and take the average of that, you get something called the Reconstruction Error. So here are the QCD events. They're this gray distribution. So you see there's some events that are, you know, images that are reconstructed extremely well, right? Not perfectly, because it's not at 0, but quite close. There is some tail, right? There's some QCD jets that the images don't get reconstructed well, but, you know, large part there is a good reconstruction. Okay, Now, if I give it a top, jet that has three partons in it, or here there's another example of a gluino that I think decayed through R parity violation, so has essentially three partons in it as well. You see that their reconstruction error, if you put it through the same thing, is much higher. Okay, so the key thing of this being model independent is that you only trained on background events, but you can of course apply it to new physics events that it hasn't seen. And if it has features that are not in QCD jets, we expect that the compression would not have learned to look for these features and then decompress them. And so we'll have a larger reconstruction error. Okay, so if I wanted to flag anomalous events, I would say, oh, maybe cut at some high, look at the tail of this reconstruction error, and if look for kind of a feature that doesn't look like a falling feature here, right? So an analogy is like, there's Google or many other Facebook will have developed really good image analysis techniques, right? Like, so they can see like, oh, here's a cat in this picture, right? So, this kind of architecture of a convolutional neural network, the CNN, is actually, part of the way in which that has been gotten so successful. But, the analogy is if you trained it on cat images, it would learn, oh, cats have, ears of this rough shape, the eyes like this, and then it'll be able to decode it to a good approximation. But if you give it a dog, the dog might have longer ears, might have a longer face. Those things will be there, but maybe not quite in the features that this thing has been trained to on cat images. And so when you put a dog image, the dog will look a little funny, maybe it will look a little bit more like a cat. And when you compare the images, that it would flag a dog image as being very different in the terms of the output compared to the input, right?
Hi, can I ask a question here?
Yes, absolutely.
So I have two questions here. The first one is that in this reconstruction error plot,
yes,
do you include the background noise, for example, the pile up or MPI and so on?
I think it depends on the analysis. Here, I don't think there was. And one of the things about pileup is it will tend to be pretty uniform, right? Yes. Whereas these things really look for kind of like edges and features, right? So you can see this thing kind of notices, oh, there's this kind of sharp borders roughly, right? And it reconstructs those well. And so I don't think pileup is a serious concern, but it would be something you could include if you want. What was the other question? Was there another question? Well, I hope I answered that.
Yeah. The second question is that in this autoencoder,
yes.
Can he learn that this autoencoder learns some key features to reconstruct this image very well? How can you figure out that autoencoder learns some key features to distinguish the signal or reconstruct the signal very well?
Sorry, you mean key pictures? Like you want to say like, oh, these ones are the ones that are interesting? Is that what you're saying? Or
yeah, these key features that to help the reconstruct the image very well.
To help
so the dimension that in your in your layer, that how many node that you need to reconstruct this image very well. So number of the
I see. Like what is actually what's the autoencoder's kind of like structure and stuff like that?
Yes.
Yeah. So let me just jump ahead and go down. So this is the picture of the one we use. This isn't the Rutgers one. So we have a 40 by 40 image. And you run you have these kind of flexible filters that, have parameters that you can train. So where you kind of take the filters and you do matrix multiplication. The idea is like certain types of matrices might find vertical edges and, some might be horizontal edges, but you don't want to presuppose what they are. So these are trainable. and you go through a couple of ways. Then you do certain things to kind of make this a tractable problem, like you reduce the size of the image by, like this. You do more filters, and then you finally
so
have.
Here in the latent space, you have 32 nodes, right?
Yeah, so we have 32. Yeah.
It is optimal. You tested or?
Yeah, I think we were looking like it. I think when if it was too small, we didn't get good performance, and we kind of went up until we kind of saturated it. And so that's kind of how much.
Identify the 32 kind of there are kind of 32 key features that represent this QCDJ very well. So is this number of 32 related to some features that we may try to understand in the QCD activity?
Yeah, I mean, you could certainly look at them, and there's some people who have kind of have better ability to kind of figure out like what these kind of this latent space is, because effectively this is kind of saying something about what are the key features to compress and then decompress, but it's kind of, I would say, a little bit hard in general to do that. I haven't had much luck, and so this kind of more iterative approach is how we're doing it. But yeah, we did do some some changes of this to try to get performance that was similar to other people's autoencoders as anomaly detector, and so there has been some amount of fiddling for that.
Okay.
All right. Yeah, thanks for the questions. So let me just go back. Okay, here. Right, okay. So, okay. All right. So we want to, modify this this faucet technique to anomaly detectors, and as I alluded to, there are kind of interesting questions you can make, ask about the mimicker. So here we're using a publicly available data set of signals and background. So in this source, they are R equals 1.0 jets, and we're going to make this PT cut. So the background is just dijet events where you look at one of the jets of this in this R and PT range. The signals, there's really 8 versions with 3 kind of classes. Okay. But roughly, the idea is that these have a variety of jet substructure, 2, 3, and 4 prong. So kind of go increasing amount of prongs of the jet substructure. The first one is a W jet, where the W is produced in the decay of a heavy particle about TeV. It decays into a Z and a W. The Z decays invisibly, so it's not part of the jets. The W decays into 2 jets. So this is like a 2-prong, highly boosted W jet, where there's some changes in the kinematics because we changed the mass of the W here in this data set. So there's kind of like a standard model one and one that's a little bit lighter, and then 2 heavier ones. Okay, so there's really one class here with 4 versions of it. Okay, and as you change that mass, it's going to kind of broaden the kind of the 2-prong aspect and stuff like that. There's top jets, so these are more like 3-prong events. Here they produced it with a Z prime, also about a TeV, decays into 2 top quarks, which decay hadronically. There's a standard model-like value and also a more lower mass value. So that's the 3-prong one. And then the Higgs Jets, which is actually very kind of beyond the standard model-like, because you produce this pair of these heavy Higgses, the capital H. It decays into 2 light Higgses, and those light Higgses decay into 2 jets, 2 quarks. So the heavy Higgs mass is 174 GeV, and the light Higgs mass is either 20 or 80. So the 81 is, in the capital H rest frame, these little H's have very little momentum, and so when you boost, you get like a 4-prong kind of jet. The 20 is a little bit, I think it's probably somewhere between 3 and 4 prong, just because the kinematics are different. Okay.
Sorry, can I ask a question?
Yeah, sure, absolutely.
So here the PT of the jet is like this W, for example, or top or Higgs, right?
Yes, that's right. So
Yes, and are you betting the mass of the W or top or Higgs? Is there any reason that you're betting this mass? Because if you're betting the mass, then the distance between the hot core we're betting, right?
yes, that's right.
So what is the reason that you're betting the mass is here?
So what we would
fixing
like,
the PT, yes.
right? So what we're going to do is that our anomaly detector, that the interpretable one, is just going to agree with the the kind of this autoencoder, more complicated one, on background events. So we want to then, after we've kind of gotten a something that imitates pretty well in background events, we want to see how does it compare with the autoencoder when looking for these signals. And so the amount of variety here is a bonus here, because we want to really throw a large amount of signals at it and see, was the kind of mimicking on the background ordering going to transfer to signals? So does that answer that question?
No. Okay, so what's the main reason that you're betting the masses of W top or Higgs?
I mean, first of all, this was their samples.
Yes, yes.
But what we wanted was just a variety of jet substructure signals.
Okay.
And then the autoencoder can find, to varying levels of success, these different signals. And we want to see, when we compare the kind of our mimicker of the autoencoder, does that transfer to the signal events?
Okay.
Right, so you might think like, oh, well, there's no reason for this to work, right? Because it's only learned to order on dijet events. Why would that necessarily transfer to things with 2, 3, and 4 prong? And I think that's what really got us interested about this, because it wasn't clear if it was going to work. You'll eventually see that it agrees to some extent under certain comparisons, but it wasn't even at all obvious that would happen.
So if I guess, and if I look at your paper,
yeah,
then if you increase the mass of this W or top Higgs,
yes,
then the distance between these prongs increase with a fixed PT, which is really looks different from the QCD jet, right?
Yes. Yes.
And while the mass of this W top or Higgs decrease, then the distance between this hot core or the prolong will decrease, so that it looks really very similar to the QCD background, right?
That's right. And so some things will be hard to distinguish, some will be better and more easily distinguishable. But the idea is, can we, it's not that we are trying to make our lives harder. We're just trying to give it a lot of different things to kind of say, oh, what if it was this scenario? Would it be able to find it as well as the autoencoder and compare?
Okay, thanks.
Yeah. Okay. So here, just to show you some of our, I'm not going to go through pre-processing, because we really follow what a lot of people have, kind of standardized, of kind of rotating so that, like where the hardest part is, right? And all this. So you could read the details. But here, you can look at sample jets. The background is kind of this sparse image. The ADG VW, maybe you can see a kind of a very hot area here. The top kind of looks like this. The Higgs is kind of some broad thing. So, these things are certainly distinguishable, but they're hard kind of event by event. If you look at the average jet event images, you can kind of see these features kind of borne out a little bit more kind of on average. Okay. All right. So we built an autoencoder to look for these different signals. And here, this is the same thing as the reconstruction error, the log of it. And so here's the background, the QCD events. And we do see that for the different signals, they are farther to the right. And that as the things that are reconstructed better tend to be QCD jets. Right? And the things that are more poorly reconstructed tend to be these new signals. Okay, so we compared some of these, our performance to, that public data set has some analysis, and we compared some of our metrics. So one way to get a metric for this is, as I vary the cut for a certain signal, right, I'll have a signal efficiency and a background rejection, right? So here, as I vary the cut for reconstruction error for the ADGVW, I get this kind of plot, this trade-off between signal efficiency and the background rejection, right? So 1 over the background efficiency. And so if you want a very good anomaly detector for any of these signals, they should be to the upper right, right? Because you want a high signal efficiency with a high background rejection. Okay, so to kind of quantify how well it does as kind of a sliding cut, you can do the area under the curve, which is just integrate this curve under here. If it was 1, it would be perfect. And that would be, so that would be the perfect, classifier to find that signal. And if it was 0.5, it would be pretty poor. Okay, so you can see that here, the W is actually the hardest of these 3 signals to find for the autoencoder. And that does agree with this, this other analysis from the this publicly datable, the people who provide the public data set. Whereas the top and the Higgs kind of have more, separation power from the back. Okay. Okay. So we're now going to mimic the anomaly detector, kind of mirroring. I'll try to go a little bit faster.
I'm sorry. Can I ask one?
Yeah, no, go. What's up?
Yeah, so here, go back to this slide, that W and Higgs.
Yeah.
So, okay. Here, W to the 2Z, 2 prolong, right?
Yes.
And this Higgs also 2 prolong, right?
But the Higgs might have, so the Higgs again comes from this kind of cascade decay.
Yes, but still, if the Higgs jet is 2 prolong jet, right?
The Higgs, so here, for instance, if, so this was, the one I was plotting was the 80 GeV Higgs, right?
Yes.
So here, the 80 GeV Higgs, right?
Okay,
you see this capital H.
Okay, so
it
sorry.
Doesn't give
so
much.
this 4 prolong, okay.
I think it's more 4 prom, yeah.
Okay, sorry.
Okay.
Okay, thanks. Yeah.
Yeah, no worries. Okay. Okay, good. So that, yeah, I think that roughly explains why this is a little easier, right? Okay. So we want to mimic the anomaly detector, and we kind of came up with 2 approaches. So the first approach we called a paired neural network, or PNN. So it takes 2 events, right? It's going to take energy flow polynomials from event 1, energy flow polynomials of event 2 that we're going to iteratively build up, which they are. And they're going to come out with an output for each of those events. So there's a deep neural network here that is trying to get a kind of a number for event 1 and a number for event 2. At the very final thing, we take the difference of these and put it through a sigmoid. And so the idea is, well, if output 2 is bigger than output 1, the sigmoid will push it to 1 if there's a big difference. And the other way, it would push it to 0, right? And so here what we're going to say is, if we know how the autoencoder orders things, that if the autoencoder thinks this one's more signal-like than this one, this truth value of this should be 1, and if the opposite, it should be 0. So the logic of this is to try to take 2 events, run them through the same interior model. So these have the same weights, top and bottom. So it's symmetric, so that if you flipped them, then this would change the, when you take the difference, it would give you minus of it. And so it doesn't matter the ordering to kind of tell you how far apart they are. So it's going to be trained to order events like the autoencoder. Then we have another approach where we just have a deep neural network to take 1 event and try to output the autoencoder's reconstruction error. So the truth value here is actually we try to do the log instead. It seemed to be easier to do. We try to match the log of the autoencoder's reconstruction error for that event. Okay, so they're just 2 approaches. Each way you're able to define if one event is more signal-like than the other, but they're just done in a different way. Okay, so this is our kind of the comparable thing as what the Fawcett analysis had when we're trying to build our mimicker. Okay, so again, let me emphasize that we're only looking at the QCD dijet events, right? We're going to later apply it to signals and see how it works. Okay, so here is the ADO as we go through the iterations. Again, just like they did, we have iteration 0, we have a neural network that has the jet mass and the PT of the jet. Okay, and we build up the number of the energy flow polynomials in the same way, right? We figure out, oh, does which energy flow polynomial is good at describing the decision ordering of the autoencoder on background events. And so I'll explain why this is kind of flat for a little bit, and then it spikes up and then plateaus again. Okay, so this is the two approaches, the PNN and the HLN, and the spread is kind of our sampling of over evaluating the ADO over different event pairs. Okay, so here, just so we don't go through all of them, this is what the EFPs are picked at each step. So the first one we get is this kind of barbell, or kind of this circle kind of shape. Okay, the second one, we actually get two circles. So it's really the square of this, this energy flow polynomial. The third one, we get a new thing, right? Besides this circle, we get this thing where it's kind of a lollipop on top of, right? And then 4, we get this barbell here, and we still have two circles here. And then 5, we get the barbell by itself. Okay, so I can understand why there's no real improvements between 0 and 1 and 2, because secretly this energy flow polynomial is proportional to the ratio of the jet mass squared divided by the PT of the jet squared. And then EFP2 is actually secretly the square of this, right? It's just these two circles. And so this neural network already has this, the information of the ratio here, right? Because it's a deep neural network. It can form the ratio of this if it's a useful property. And so there's no benefit from adding these. So this is showing you some of the problem with the technique of comparing the ADO of the thing I want to mimic to the energy flow polynomials linearly, because you might get redundant information, right? 1 and 2, even though it works on the mispaired events, it doesn't really help in the improvement of the mimicker. But here, by the time the third iteration, we do get this new energy flow polynomial. So we get a substantial jump here. Here we get one more, right? We get the barbell here, we get a substantial jump. And actually, so 5, we do still get an improvement. So it's a little bit, I think it must be that, somehow this wasn't, the neural network wasn't able to, pull out just the information this alone. Maybe it was some, the training wasn't ideal. I think in principle, iteration 5 should be the same as iteration 4, but it has improved. So iteration 4, I suspect in training as well. And then we plateau. Okay. The result that we think is the best we can do, because we generated all the energy flow polynomials with 5 edges, is we just threw in all of them without worrying about which is the most important, and we get this performance. And the spread in this should actually be similar to the spread here. And so this, I think what we think is that we've saturated the performance here, that essentially there's no better performance than that. Okay, so we didn't do as well as the faucet analysis. We only got to ADO of about 0.83, but doesn't stop us from trying to see if this is effective as an anomaly detector. So we'll do that in just a second. But we can get some insights on QCD from this result. So we went through 14 iterations. So we selected 14 energy flow polynomials. These are all the graphical depictions of them. But if you look at them carefully, there's really only 6 prime ones. They call them primes because this one is really the product of 2 of these, right? The two barbells is equal to this barbell squared, right? And so you can certainly see that many of these are composite in the sense that they have prime factors within them. And of these 14, there are only 6 prime factors. There's the barbell, the circle, this 3-dot line, there's this lollipop, a triangle, and then a 4-dot line. Okay. Okay, so we can already learn a little bit about what the information that's needed to kind of order like the autoencoder on QCD events. So here I drew in a different way where I put in colors. so that I've used the minimum number of colors to draw, to color in the nodes so that any two connected nodes don't share the same colors. This is like the map coloring problem, except for graphs. And this is called the chromatic index. So every one except for this triangle needs only 2 colors. This triangle needs 3 colors. So in terms of an energy flow polynomial, what this tells you is that if you have, chromatic index 2, you actually need a 2-prong event before you get any non-zero value. Because if it's a 1-prong event, all the angles essentially are 0, right, from that prong. And so if you had a 1-prong, jet, you would get a very small, value for this energy flow polynomial. Okay, so all the chromatic index 2 objects need 2-prong events or higher to get a non-zero value. This, this chromatic index 3 needs, 3 prongs or more. So we kind of understand now from QCD that what's being used by the autoencoder, it's, what you might expect, that the type of information that's needed to determine how poorly something is reconstructed by the autoencoder is, if it has, needs 2 or more prongs, essentially, right? Oh, sorry, so I went the wrong way. So this autoencoder, since it's been trained to do well in QCD events, which it mostly sees 1-prong jets, maybe some 2 prongs from some splitting, it mostly reconstructs poorly the 2-prong and higher. Okay, so we kind of expect that, but we get some more information on people, for people who understand more about the energy flow polynomials, this gives you some insight into the things. And actually, so when we first shared this with Jesse Thaler and Dan Whiteson, Jesse was pretty, interested in the energy flow polynomials that was generated because there were some QCD power counting rules that they were developing for energy flow polynomials, and the factors we were finding were the ones that are expected in QCD. Okay. So let's now move to the question that's kind of, I think, the really kind of interesting aspect of this. Do these detect anomalous events, right? So certainly the autoencoder has been designed to do that, but do they kind of have similar performance? Okay, so here again, like we showed this plot before, that the autoencoder can distinguish QCD jets from these 3 signals, right? And so again, the signals are more to the right. If you look at the equivalent anomaly score for our last paired neural network, the signals are to the right, as they should be. Same thing with the high level network. They're 2 different, techniques, but they have, the same kind of separation power. You can then plot the ROC curve, and you can see kind of that, these are, so the dashed lines are the high level network, the paired neural network. And so the dashed lines are better at background rejection, high signal efficiency, but eventually lose out when you go to lower signal efficiency. So they are actually pretty good if you were working at high signal efficiency, but eventually lose out to the autoencoder when you go to lower signal efficiency. So here you can kind of see that, because here there's a nice kind of sharper drop of the background, right? It's lower signal efficiency because as you go to the right more on the cut. And here you can kind of see that, there's more of an overlap with the signals of the kind of very end of the background. So that kind of explains why we get this behavior. So we can compare these. So let's look at one signal and look at this area under the curve metric. So here we see the autoencoder has this area under the curve. Here is the paired network and the high level network as you go through different iterations. And you see by iteration 4 or so, it's actually got very good agreement in terms of the area under the curve. Okay, so I think we were just really kind of excited about this result because we had no idea if this would transfer, the ordering of background events would transfer to kind of ordering between signal and background. And it does seem to at least agree with this area under the curve. We'll have different comparison later, which doesn't look as good. but at least for area under the curve, it agrees quite well. And it looks like you only need a few energy flow polynomials to get there. Okay. Now we have 7 other signals, so we should now check. And here we thought, oh, this will never work. But at least for area under the curve, it works quite well, right? So some actually get better and then kind of get back down, right? Because it's trying to order better, so it's going to get closer to the, the autoencoders AUC. Some don't quite get as good, but for the most part, they either get close, right? Or, I would say that this one, 20 GeV Higgs, 59 GeV are the kind of the worst. But these 3, or actually these couple are better. These ones asymptote to the same value essentially. And if you always to choose which of the techniques were a little bit better, it looks like the paired neural network is slightly better at getting performance as an anomaly detector. So we were really quite happy with this. Out of 8, 6 are as good or better, at least in terms of area under the curve, and 2 are close, but not quite as good. So I think this was a very non-trivial result that, we just did not know what would happen. Okay. So here's the comparison that doesn't look quite as good. I've already alluded to it, is that if you go to, smaller signal efficiency, then these mimickers are not going to do as well. So here, let's look at fixed signal efficiency at 0.1. What's the background rejection? Autoencoder gives, about 20, 1 out of every 27 background events. It takes only 1 every 27. Here for the high level network and the paired neural network, it takes, every 12 or 11. Similar things, kind of across the board. It rejects, almost, it takes 87 to get 1 background event at the signal efficiency. It only takes 28 or 38. There's some that are slightly better, like the 80 GeV Higgs, but it's, for the most part, if you go to low signal efficiency, these do worse at it. So that's certainly something that if you look at not a global kind of thing like the area under the curve, but you work at like a fixed signal efficiency, and look at the background rejection, or do it the other way, look at the fixed background rejection, look at the signal efficiency. It doesn't do as well, and we recognize that. Okay, so sorry for running late. Let me conclude. So it's possible to adapt this technique to design understandable anomaly detectors that are simple, that rely on only a few high-level physics variables, so they're more interpretable. And I think the very non-trivial result is, even though we don't order that well on background events, right? We only got to like 83% on the ADO. It seems to transfer to, the comparison between signal, to use as an anomaly detector. So I don't think it's, it allows a much simpler yet effective, especially if you're just using, AUC or at higher signal efficiency anomaly detector. And we did learn, I think, a few insights about QCD, because we see particularly what type of energy flow polynomials are needed. And actually, there were these 6 prime factors that are kind of the crucial aspect of it, to figure out if a QCD jet image will be flagged as anomalous by the autoencoder. Okay, so there's a lot of directions that we're trying to explore in this. First question is, we never got great agreement on the ADO. And we want to understand, is that something about the set of energy flow polynomials we use? So we didn't quite use as many types as the faucet analysis. So maybe that's what's the problem. And if we can kind of get a better agreement, will this improve the performance at low signal efficiency? Will that allow us to kind of rectify the problems with our more simple interpretable anomaly detectors? We've also kind of seen many kind of, inefficiencies and kind of redundancies when we were doing the procedure from the faucet analysis, right? We saw, the same prime factors appearing again and again. And so is there a way to kind of make this more streamlined so that we don't kind of, train neural networks that are just using the same information? And so is there a more efficient way to do that? Should we be kind of only, using energy flow polynomials that have new information, right? To make this instead of these plateaus and stagnant kind of improvement, can we make that go better? We would like to also apply this to other anomaly detection approaches to jet substructure. I think it would be very interesting to see, will we find other energy flow polynomials that are interesting, in terms of explain the background ordering? Would that, lead to potentially better kind of anomaly detectors for jet substructure by kind of combining things? And then finally, I think something that's really an open question is jet substructure is very useful because you have this nice basis of the energy flow polynomials. So a basis for what you could use to mimic the neural networks that we're trying to mimic. But can you use this in more general cases where there is no obvious basis of observables? So I think that's a very open question. I think in some cases it might work, but I think it really has to, some thought has to go into what type of scenario to look at here. Okay, so let me conclude. And I just end on this kind of provocative, picture. You have this kind of, this robot. You can look into the brain here. Is it something similar to this? We're trying to do the same thing essentially for these anomaly detectors. So thanks for your time, and happy to take any questions.
Okay, thank you very much for the nice talk. Are there questions or comments?
Yeah, I've got one. I'm confused about these curves with the signal efficiency and background rejection and the AUG you consider. So
This
if I'm right.
Okay, yeah.
If I understand correctly, you generate these curves by taking your distributions of the anomaly score, putting a cut somewhere, and then sliding this cut and
Exactly.
see. Okay, great. So why am I interested then in the AUG under this curve? I mean, for a real analysis, you would essentially decide on one particular cut and then use whatever signal efficiency and background rejection you get for that cut.
Yes.
And essentially, as long as this one point works very well, I don't really care what happens for other choices of cuts. So why is this AUG relevant for this curve?
Yeah. So right. So that's why our paper is under review, and so it was recommended that we also provide the table that I showed about fixed signal efficiency and fixed background rejection as a different comparison. And so that's why we provided that. The reason why you do the area under the curve is it's a common metric that people utilize in machine learning. So often people will just compare area under the curve to kind of get a kind of a global sense of how good of a classifier something is. And it also tends to be, it does tend to be a little bit less sensitive to kind of fluctuations. So, and I always forget this, there is kind of there is an interpretation of what the area under the curve is in general, but I've forgotten it. So, so often you'll just be kind of a figure of merit. So I think it's largely due to its ubiquity and it's as a way to compare. But I agree that if you're going to use this for an analysis, you might want to use something like in the table.
So how would you, if you wanted to do an actual data analysis, how would you decide on which point to pick on the curves?
Yeah, so this is actually something that I don't think there's been enough discussed in anomaly detection, is that, of course, anomaly detectors are supposed to find any signal, right? And so really you should only be talking about the background rejection. You're going to work at some background rejection, right? So you should essentially just say, well, I'm going to take in some amount of the background here of this gray curve and look for interesting events on the tail, right? by doing a cut, like say looking at here, right? But it's a way to kind of flag, oh, if I see some, if I trust the distribution, you could see, oh, is there some kind of shape change as I go to higher anomaly score? So it's a little bit less that you would actually use a particular cut, in my opinion, because it's really just a way to find interesting events, right? It's to say that, well, I don't expect many events on the kind of tail of this distribution. And so I should just look at the kind of, the events at higher anomaly score. And so that's why one reason why maybe thinking of signal efficiency is not the right kind of thing to think about, because of course it could be some other signal. It doesn't have to be any of these signals, right? But you want to compare, the mimicker to this autoencoder, because at least these are signals we know about.
Okay.
That kind of answers some of it. It's a complicated issue.
It sounds a bit like you want to do kind of data analysis by eye in the end. I mean, that's not what the experimentalists do. They should do some serious statistics, no?
No, I agree, and I think it's not. I don't know. Well, actually, I don't know what so it'd be something that I think has to be followed up. It's not something that you can just say like discover new physics, in my opinion, just in the first use of this. I think you would use this to flag certain events to be interesting. And then you could like think about like, oh, what kind of new physics signals might give that. But then that might design future analyses that you would use on new data and not try to just look for anomaly, right? Obviously, if you just look at a certain data set enough, you're going to find funny things in it. I think this is kind of the beginning step of something moving towards kind of directing you towards an interesting scenarios.
I see. Okay, thank you.
Yeah.
Can I ask a question again?
Yeah, sure. Absolutely.
So can you go to this performance plot in terms of the iteration for the various methods of the, yes.
This one?
Yeah, here, yes.
Yeah, okay.
So here, if I focus on the 20GB Higgs,
yes,
then this performance degraded in terms of the iteration, unlike the 80GB Higgs or 80GB top, right?
Yeah.
So how can I understand this degradation in terms of the iteration for the 20GB Higgs?
Oh, so how do I understand that this 20 GeV Higgs is kind of goes like this and it goes down?
Yes.
Yeah.
Unlike
So
the top, yes.
I think what must happen is, as you get to iteration 5, the decision ordering improves, but it's not perfect. So it really depends on how that decision ordering on background events transfers to signal versus background, essentially, right? And so when I try to get a better, high-level network or paired neural network to order better on background events, it's not guaranteed that it's going to transfer to all events. So even in, I think I'm not even sure if I get, the decision ordering on background events very close to 100%, that I'll necessarily converge to this. It's not clear to me yet that was the case. It seems suggestive, right? Because these things do seem to be getting closer, right? Every time you get to iteration 5, it tries to correct towards it. I guess here not. I guess they all kind of correct and maybe overcorrect one way or the other. And so I think it's just that there are new features in here that I think if you want the anomaly detector is somehow ordering differently than my mimicker. But yeah, we haven't thought carefully on like, is it the kinematic features here that are happening that are causing these aspects? I think we can come up with some theories, but we haven't thought about that in any kind of conclusive way.
Yeah, it's just difference is just mass between the 20 GB and 80 GB Higgs, right?
Yeah, so
semantics,
but there
yes.
is a difference in the, as we were talking about. So here the 20 GeV Higgs, the heavy Higgs is 174 GeV. So when the 20 decays into two 20 GeV Higgses, there's a non-trivial amount of momentum in the center of mass frame of the heavy Higgs, right? So now I boost that heavy Higgs. So this thing that has a Higgs jet this way and a Higgs jet this way, when I boost to the lab frame, it might not have 4 prongs in it, right? It might have maybe 3 prongs in it because one of the decays here goes in there. So here I think it's there, you can kind of understand why there's such a stark difference in the AUC, because this is a 4-prong event, so it's very different from standard model. This one I think is probably, maybe it's not even 3-prong, because here you see the top is much very different, right? So it may be that actually that this is more 2-prong. So I think it's this kinematics that's causing it. We didn't get exactly the same AUC numbers as this analysis on the public data set, but we were close. So essentially we were getting very similar results. So I think our autoencoder is picking up on the same stuff that theirs was.
Okay.
Can I ask a question? I think I
Yes.
missed. So you are the mimic the signal efficiency plot of mimicker.
You're talking about this?
Yeah, this one. So
Okay,
here, mimicker has better performance at high signal efficiency, right?
That's right.
Yeah, that's kind of general feature. So that's what this general feature follow from.
Where does it follow from? Yeah, so I think it's because here you see that there's this kind of in the autoencoder. So if I want the low signal efficiency, I'm essentially making the cut close to the end of the signal distributions, right? And so here you see that there's a good separation between the end of the signals and for the autoencoder from the background distribution. If I do the same thing here, I think, except for the blue one, I see something very different. Like for the green one is, I think, a good example here. The green one, the signal efficiency, if I cut it here, I still have plenty of background events to the right of it, right? So here, that explains why the green is actually so poor here, right? Because, I don't reject that much background, even if I cut out almost all the signal. But the blue one is better, or you can see that the blue one is better until you get to like signal efficiency of like 0.1 or so, right? And you can see that there, it's like the blue is, if I cut like here, maybe I get 10% of the signal, but there's already a big drop in the signal, the background, right? We rejected a lot of the background. So it's really just the kind of this low, kind of the high anomaly score behavior of the signal compared to background. But if you go to large signal efficiency, you're starting from kind of over here, and you see that we do better there because there's this long tail of background that we get to reject while keeping all the signal, right? So that's, I think these two ends of the distributions explain this behavior. Why you get that, I don't know.
Yeah. Okay.
Yeah. So sorry, I can explain. I can explain. Yeah, why the plot comes out like this based on this, but yeah, why is that? I mean, it may be a generic feature. I might hypothesize that it's a generic feature because there's many kind of inputs and outputs to generate this anomaly score. Whereas here we're really only using like, the 6 prime factors or like, 14, right? So compared to like 1600 inputs and 1600 outputs to compare to, we're trying to take, only a couple of numbers in comparison and generate an anomaly score, right? And so it may just lead to this kind of larger, spread than there is here. But yeah, I don't have any better answers than that. I think it's an interesting question, but yeah, I think it'll depend on like, as we get better performance, if it continues to persist like this, then it may be a generic feature, right?
Oh, I see. So I mean the position of this intersection is also kind of hard to understand. I mean,
Oh, where this intersection
yeah. I mean not this. I'd say. Yeah, from the graph we can see that. I mean the feature of was WMS from which WMS with W boson properties of W boson makes this one or kind of that understanding.
Yeah, I think I mean, the crossover is just, yeah, and actually it's probably harder to, if I did epsilon B, then you would just say, oh, they cross over when like, you know, the integration to the right is the same for both distributions, right? So it's that crossover point. 1 over epsilon B, I don't have as good of a intuition on what that means when they cross over.
Okay, thank you very much.
Yeah, you're welcome.
Maybe a too naive question. Do you
Okay.
also consider 125 GeV Higgs?
Oh, the 125 GeV Higgs. Yeah, we were just using this publicly available data set. We didn't want to go and generate our own, basically. It was just kind of nice to use this. Yeah, so for instance, like it'd be interesting to apply this maybe to like a boosted Higgs recoiling off a W or something like that, right? And seeing how it works. I mean, I imagine it would be kind of similar to this, maybe. Although this is pretty, I mean, it's close. I mean, I think some of the you know, the boosted Higgs searches are kind of like maybe around, around 400 GeV in terms of PT. So I think this isn't that far off from it. This is probably the closest thing that, you know, would mimic that maybe, but I'm not, that's just a guess.
Okay. Are there further questions or comments? Okay, if not, we may thank Professor Chang again. Thank you very much.
Yeah, no, thanks so much. It was really nice to interact with all of you, and hope to see you either virtually or in person in the future.
We hope so too. Okay.
Yeah. Okay. Well, take care.
Take care. Bye.
Bye.